Welcome to the course on Introduction to Electrical Engineering. We have a lecture 15 today on 3-phase AC circuit part 1. Coming with the outline of presentation, we will start of course introduce the topic with the applications, and we will talk about of course the shortcomings or disadvantage of single phase system. We will talk about advantage of 3-phase system, and we will talk about balanced 3-phase system, and of course the different connections like star star connections, the star connected source and star connected load. Then we will talk about similarly star connected source and delta connected load, and delta connected source and delta connected load, followed by like a delta connected source and star connected load. And then we will talk about line and phase quantity in 3-phase circuit, and followed by unbalanced 3-phase system with numerical problems like. So, coming to with an introduction, that when we refer to a sinusoidal source, we picture a single phase sinusoidal voltage or current at its amplitude, frequency and phase, which we already talk about and shown in the left side here. Here we like to discuss polyphase sources with the 3-phase sources in particular, as it is covered on the typically on the right side the waveform you can see. So, that is a 3-phase waveform like. So, to start with, I mean we can say the polyphase system were independently invented by several inventors in the late 80s, 800s, and the 3-phase power involved out of electric motor development. In 1885, the Galileo Faraday was doing the research on rotating magnetic field, and Faraday experimented with different types of asynchronous electric motors, especially induction motor, and the research and his studies resulted in the development of an alternator, as you can see the typically the kind of figures from here. Now, of course, Nikola Tesla has gained a US patent for a 3-phase electric motor design in 1887, and figure shows that the Tesla expected his 3-phase motor being powered from a 3-phase generator via 6 wires, as you can see the figure here. And of course, later on with the war of currents, the AC power has become predominant and is still being used around the world, and some of the application of 3-phase power system are shown as follows. Typically 3-phase systems are used in high pressure centrifugal electric water pumps, normally used for agriculture, then drinking water supply, many even including the your aqua farm. So, many places we require the you can call it the irrigation. So, for that purpose use this pump of both surface mounted as well as the submersible pumps like. Another example is here like a 3-phase electric arc furnace. They are of course used for typically for melting the many metals like including the steel and other metals, where we require large amount of power for the purpose of heating, and that for that we use this 3-phase electric arc furnace. Why we have to go 3-phase? Because the power level is quite high in this case, from is goes to like a few hundred kilowatt order of that. Then we have a like a typically 3-phase diesel generator set you see around, maybe small rating, we have of course not very big size like 25 kVA, but for large rating it goes even typically you might have seen even around go to even a MVA rating, because they are used for as a emergency power supply when supply is not there, or they are also used in a place where the supply is not accessible, like a telecom towers, large number of telecom towers. So, most of the telecom towers like in India we have a 4.5 lakh telecom towers. So, every telecom tower have a DG set, and most of the you can call it residential building as well as commercial building have a DG set for providing the you can call it the uninterrupted power for the supply system, especially the you have many emergency loads, typically the lifts in several buildings, you have to provide the certainly the emergency supply or uninterrupted power supply. So, where there of course, for a small backup can be achieved by some other means, but for longer duration for even starting from few minutes you require certainly the DG set. So, you will find wherever the your electric lifts are there, you will find the DG sets are already there nearby. So, they are also powered along with the grid, they powered by DG set. Maybe it may not be operational for longer time, but certainly you cannot take the risk of the human life in such applications such as electric, typically the electric lifts also. Then the other example is heating ventilator and air conditioning system, typically chiller motors. I mean, we use these large motors for the purpose of refrigeration, air conditioning, and many not only heating and air conditioning system, they are also used for refrigeration system. And typically for such applications, sometimes the motor rating is very substantial or quite high rating, even the motor goes sometimes the megawatt rating also in those applications like. Then you have a typically air conditioning with the heavy duty blower motors. So, these are the part of the HVAC system like including blower motor, or you have a typically like heat pump motors. So, all these are the typically part of heating, ventilation, air conditioning system like. So, plenty kind of motors are used for different purpose, like also, and or you have a like a typically exhaust fan motors, as you can see the exhaust fan for again for ventilation purpose. That is also part of your heating, ventilation, air conditioning system, or you have industrial air conditioner, air cleaner or purifier unit of 3 phase of large rating. Then you have a industrial refrigerator compressed air dryer unit, again because these are of large rating. So, we have to powered with the 3 phase motors. Then industrial water chillers plant. So, because they consume a large amount of power, that is why we have so many typically motors in those plant like. Our 3 phase motor are used in many electric power trains to drive your electric vehicle, which are coming up like in around the world, and Tesla Model S rear drive motor use the 3 phase induction motor. So, the typically electric vehicle is one of the interesting application for 3 phase motors of different variety. The electric 3 phase double stack convection oven, then your aluminum foil rolling mills. Rolling mills certainly needs a lot of synchronized motion, so use the motor for that. Then you have a wind turbine generator, that is also normally 3 phase, or you have a 3 phase screen printing machine, then 3 phase carbon dioxide metal laser cutting equipment, and you have a semi automatic 3 phase cotton sticker printing machine, or 3 phase motor driven used for conveyor belt, or 3 phase textile stitching machine utilizing 3 phase servo motor. Then Acb base of course 3 phase locomotive. Nowadays we have a locomotive with the 3 phase induction motor, whether it is your electric train or whether it is your metro. So, all where we use the 3 phase supply with the 3 phase motors. It may be powered from single phase supply, but finally the drive motor always are 3 phase. So, we convert like of course single phase to finally for 3 phase to drive the 3 phase motors, because those are more efficient. We will talk a little later about that. Or you have a 3 phase on grid PV inverter. Now, coming to of course this supply system, first we talk about like we have a single phase system. Single phase system consists of a generator connected through a pair of wires or transmission line to a load, as you can see here, and Vp is the RMS magnitude of the source voltage, where phi the phase angle of the voltage. So, this in single phase system it contains 2 identical source equal magnitude and same that are connected to 2 different loads by 2 outer wires and the neutral sometime. Or you have generally we have a polyphase system. Polyphase means more than one phase, it can be any number of phases, but of course, out of polyphase we adopt normally the 3 phase system. So, circuit or system in which the AC sources operate at a same frequency, but different phases are known as polyphase. An example may be 2 phase system, 3 phase system, 5 phase system, or even much higher than 5 phase system are also use some specific application like, but most popular have been 3 phase system. Now, you can have a 2 phase system, it is produced by a generator consisting of 2 coils placed at perpendicular to each other. So, that the voltage generator by one lags by the other by 90 degree, as you can see here. But you can see why we have not adopted the 2 phase system, because you can see here we have a 3 wires, but we have only power flow corresponding to 2 phase. So, even in 3 phase we need the 3 wires. So, here you will be having the less power which is getting transmitted for 3, even using the 3 wires like also, and the many appliances have a difficulty working with the 2 phase like. So, finally, we adopt in general we adopt the 3 phase supply system, and it produced by a generator consisting of 3 sources having the same amplitude and frequency, but only out of phase with each other by 120 degree. So, since you have a 3 phase, so it should be like a 360 by 3. So you have it like typically here 3 phases with the start from 0, then you have minus 120, then plus 220 or minus 240, and that we call 3 phase supply system. Of course, sometimes we have a neutral to provide the single phase load, as you can see it here. Single phase load is provided with each phase connecting to the neutral, I mean two neutral together, supply neutral as well as or generator neutral with the load neutral. So, that we call it 4 wire 3 phase 4 wire system. And we have to make such a system, polyphase system, which can supply not only the typically the large load of 3 phase, but we should be able to supply like a single phase load. We have a lot of single phase load, most of the residential loads are single phase, and you can see even many of your office equipment also normally 3 phase. So, sorry single phase. So, they have to be powered from single phase. So, you must have a proper means supplying the single phase load from the 3 phase supply system, and normally by design we try to make it equal load on the all the 3 phases. So, that the load on the 3 phase supply system is always balanced, but that you can do design, but operationally most of the time we have unbalanced. So, we will discuss of course unbalanced load also on this 3 phase supply system, and once you connect the unbalanced load, sometime you may find some unbalancing in the voltage also caused by the drop in the source impedance like. So, now what are the of course the disadvantage of single phase system, and because of which we adopted the 3 phase system. The initial application of AC supply was for heating and heating the filaments of electric lamp, and for this single phase supply system was very satisfactory, similar to like a DC supply, but few years later AC motors were developed, and it was found for this application the single phase system was not very satisfactory. And what was the reason for? I mean typical example is single phase induction motor is not self starting unless it is fitted with the auxiliary winding, and single phase induction motor is not self starting, has a poor efficiency and power factor than the corresponding 3 phase machine, like that is another reason. I mean you have a 3 phase generator, 3 phase motors, they are much more efficient, I mean than the single phase motor and single phase generator like. So, finally, that is the reason we have gone for. So, you can see single phase motor, it does not, it is not self starting, it has a poor efficiency and power factor. Our 3 phase induction motor is a self starting, you have a rotating magnetic field because of the 3 phases, and you have a better efficiency and power factor. So, we have some of the advantage because of which we adopted 3 phase supply system. So, nearly all electric power is generated and distributed in 3 phase, and when 1 phase or 2 phase inputs are required, they are taken from the 3 phase system rather than generated independently. Even when more than 3 phase are needed, they can be provided by manipulating the available 3 phases with the help of kind of transformer like. So, because in many application, example is like aluminum industry, where 48 phases are required for melting purpose. So, we convert 3 phase supply into the 48 phases like with the help again with the help simply by the transformer static device like, and many other applications also we convert not only the 48 phases, we convert sometime 5 phase, sometime we convert 6 phase, sometime we convert 9 phase. So, this 3 phase supply system with the transformer you can convert to any number of the phases, typically more than 3 phase like you can call it. Even the 3 phase supply system can be converted to equivalent to 2 phase, which is used normally for the furnaces like, which require the single phase load. So, you can have a isolated 2 single phase load which can supply the arc furnace. So, virtually you can convert the 3 phase supply system into any number of phases starting from 2, 4, 5, I mean like. So, there are transformer connection which can provide you conversion from 3 phase to any number of phases like, and of course, for single phase you can take between line to neutral also, which are already practically used in most of the applications like. So, the instantaneous power in 3 phase system can be constant, not pulsating. That is the reason we have discussed last time that single phase supply system where the power was pulsating in nature, along with the average you are having pulsating power, but here 3 phase we do not have such a pulsating power, and that is really the beauty of 3 phase supply system. So, this results in uniform power transmission and less vibration of 3 phase machines either for generator or for motor version. So, for the same amount of power, the 3 phase system is more economical than single phase, and the amount of wire required for a 3 phase system is less than that required for equivalent single phase system. So, now coming to typical example, the generator based 3 phase generator, typically that is we talk about generation of balanced 3 phase voltage. So, the generator basically consists of rotating magnet, you can call it on the rotor, usually may be electromagnet excited by the DC supply, or you may have a permanent also. So, and stationary windings are on the stator, as you can see the 3 phase winding, and 3 separate winding coils with terminal AA dash, BB dash and CC dash are physically placed 120 degree apart around the stator. So, as the rotor rotates, its magnetic field cuts the flux from the 3 phase coils and induces the voltage in the coils, and because of the coils are placed 120 degree apart in phase, the induced voltage in the coils are equal in magnitude, but out of the phase of by 120 degree. As you can see here, Vn, Bn, Cn, they are 120 degree apart. Like Vn have a like a starting from 0 degree, then Vbn from 120 degree, and then Vcn from 240 degree. So, generator voltage are 120 degree apart from each other. Like now, coming to balanced 3-phase system. A typical 3-phase system consists of 3 phase voltage sources connected to a load by 3 or 4 wires or transmission line, and voltage sources can be either star connected or delta connected. You can just see here, you have a 3-phase generator which can be connected in star. Normally, we have a connection in star, but you need a neutral for providing the supply for single phase load also along with the 3-phase load, or you can have a delta connected, but that you can feed only 3-phase loads. Well, we can define like the phase voltage between line A and B and C and the neutral terminal, that we call it Vn, Bn and Vcn, and if the voltage sources have the same amplitude and frequency omega and out of the phase with each other by 120 degree, then the voltage are said to be balanced. And in case of 3-phase balanced voltage, the sum of all 3 phase voltage are 0. So, Vn, Bn plus Vcn equal to 0, because they are typically equal RMS value, but they are in phase displacement 120 degree. So, this relation valid for all the time, as well as this relation is valid for the currents, and if it is a balanced load, that is why you do not experience any neutral current also. And we say here the magnitude, either peak magnitude as well as the RMS magnitude of these 3 phase voltage are equal. So, we can say there is a of course, the concept here of phase sequence. The polyphase, the phase sequence is the time order in which the voltage pass through the respective maximum value, and there are normally 2 phase sequence we have in the system, the ABC sequence, or we call it positive sequence, and there is a Acb sequence which we call it negative phase sequence. And how it has been, then if we really give to some rotating motor, we can give these 2 sequence, and you will find the different direction of rotation of this electric motor. So, by changing this phase sequence, only by changing the 2 terminal of the supply across the motor line. The importance of phase sequence, it is important to 3-phase power distribution, because it determines the direction of rotation of a motor connected to a 3-phase power source. So, now we can say what is your ABC sequence or positive sequence. This sequence is produced when the rotor rotates in counterclockwise, as you have seen in the figure, and Vn leads by Vn, by which it turns leads to Vcn. So, here we can define as a typically Vn equal to Vp phase voltage, RMS phase voltage at the angle of 0, and Vbn equal to Vp at the angle of minus 120 degree, and Vcn equal to Vp at the angle minus 240, or we can say Vp at the angle of 120 degree. So, we can say Vp is the effective or RMS value of the phase voltage, and another phase sequence we call it Acb sequence or negative sequence. It is produced when the rotor rotates in clockwise direction, typically in opposite direction, and here Vn leads the Vcn, and which turns in leads to Vcn. So, here Vn, if we consider that it is Vp at the angle 0, but here Vcn now Vp equal to at angle minus 120 degree, and Vbn Vp at the minus 240 degree, or Vp at the angle of 120 degree. Only difference is the in the 2 voltage, and last 2 voltage, that is get interchanged, and which changes the direction of rotation and the phase sequence of your typically of rotating magnetic fields like now. So, this we call it negative phase sequence. So, this is the concept only in applicable for 3-phase system. So, now with an example, determine the phase sequence of the set of voltage Vn equal to 200 cos omega t plus 10 degree, Vbn 200 cos omega t minus 230, and Vcn 200 cos omega t minus 110. So, the voltage can be expressed in phasor form as Vn equal to 200 at the angle of 10 degree, Vbn 200 at the angle of minus 230, and Vcn at the angle of 110 degree. So, we notice that Vn leads Vcn by 120 degree, and Vcn leads the Vbn by 120. Hence, we can say this is Acb sequence, or we can call it is a negative sequence typically in terminology, like otherwise we say it is Acb sequence according to the voltage. So, of course, similarly you can have you can calculate here also in this typical practice problem. Now, coming to case of possible 3-phase load configuration. So, depending upon the end of application, a 3-phase load can be either star connected or it can be delta connected, and a balanced load is in one in which the phase impedances are equal magnitude and in phase. However, a star or delta connected load is said to be unbalanced if the phase impedances are not equal in magnitude or phase. So, we can say possible 3-phase load configuration for a balanced star connected load. We can say Z1 equal to Z2 equal to Z3, that is equal to Zy, because you say star connected, where Zy is the load impedance per phase, which is shown here. Then we can say typically the for balanced delta connected load, as you can see connection of delta, we already discussed all the delta and star connections. So, Z A equal to Z B equal to Z C, that is equal to Z delta. Z delta is the load impedance per phase, and impedance relation between star and delta, which already proven earlier, Z delta equal to 3 Zy or Zy equal to 1 by 3 Z delta. That we already discussed in star delta transformation, which we have a couple of lectures before. Now, coming to the polyphase possible connections, there are 4 possible connections, because the 3-phase sources and the 3-phase load can be either star or delta connected. So, we can have a connection like Y connection. So, there can be like a Y connected source and with Y connected load, or it can be Y connected source with a delta connected load, or we can have a delta connected source with a delta connected load and delta connected source and star connected load. So, all the 4 combination we can have in practice like. So, now coming to with the example with the balanced star star connection. A balanced star star connection is a 3-phase system with a balanced star connected source and balanced connected load, as you can see here, and balanced star connected star star connection showing the source line and load impedance, but all 3 are identical, that is source, that is load, that is feeder impedance, and that is of course the neutral impedance. So, but this can be equated, of course, you can write typically here that if we say define here by lumping the impedance together, Zy equal to Zs, that is source impedance plus Zl line impedance plus load impedance, that we can write the Zy here, and Zs and Zl are often very small compared to with Zl, that is load impedance, and so we can assume Zy equal to Zl if no source or line impedance is given there, and of course, we can say it is a balanced impedance network with this. So, we can say assuming the positive sequence, the phase voltage or line to neutral voltage, we define V n equal to V p at the angle 0, V p n V p at angle minus 120 degree, and V c n at the angle V p equal to V p at the angle of 120 degree in this circuit. So, line voltage, you can call it line to line voltage, or simply the line voltage V a b, V b c, V c are related to the phase voltage as V n V a b equal to V n minus V n b, or you can call it minus V a p n, that will be equal to V n minus V b n, that is in the circuit as we can explain, and if you put V n minus V b n, that comes V p at the angle 0 minus V p at the angle of 120 degree. So, when you really operate this polar coordinate, you change to rectangular coordinate. So, V p can be taken out, and you can just say cos typical the all these operator to operate here. So, it comes 1 plus half plus j root 3 by 2, or it comes typical example as a under root 3 V p at the angle of 30 degree. So, you can say the line voltage is root 3 times the phase voltage, and the 30 degree phase shift is also there. I mean, this is like kind of the line voltage get leading by 30 degree from the phase voltage, original phase voltage as a base you can consider. So, similarly, one can obtain V b c equal to V b n minus V c n, that is root 3 V p at the angle of minus 90 degree, and V c a equal to V c n minus V n, that is root 3 V p at the angle minus 210 degree. Thus, the magnitude of the line voltage is equal to V L equal to root 3 V p, that is where the V p is the phase voltage, and where we can say V p equal to V n, V b n and V c n magnitude, and similarly, V line V L equal to V a b, V b c or V c a in terms of the magnitude of the voltage. So, there is a relation of root 3 between line and phase voltage for the star connected network in the circuit like. Now, you can say how the balanced star connected concept is there. So, just to look into a phasor, you have a here the typically V n, V b n, V b n, V c n, that is a 120 degree, and when you really take the V b n on other side and you calculate the typically V a b, which is a your V n minus V b n, minus V b n is nothing but. So, if you take a resultant of that, it comes V a b. Similarly, I mean it is a 30 degree leading from V a b. Similarly, from V c a it is 30 degree leading from V c n, and similarly your V b c is 30 degree leading than V b n. And how you are getting this, that we are already explaining here, that V a b equal to V n minus V b n or V n plus V n b. So, phasor diagram illustrating the relations between line voltage and phase voltage here. So, we can say balanced star star connection by applying Kirchhoff voltage law to each phase, line current are obtained IA equal to V n upon Z y. This is single phase network equivalent to So, IB equal to VBN by ZY, and that is equal to VN at the angle minus 120 degree by ZY, and that you can call it like IA equal to at 120 degree. Similarly, for you can write IC equal to VCN upon that can be VN at the angle of minus 120 degree divided by ZY equal to I at the angle of minus 240 degree. So, these are the 3 phase currents which are also again typically 120 degree shifted from one to another, like compared to the IA and IA current. So, now we can readily infer that the line current in case of balanced load adds to the 0, again similar to like voltage we IA plus IB plus IC equal to 0, I mean here, and that is why you will have IN equal to minus, I mean here in this Kirchhoff current law applying here. So, you will have minus IA plus IB plus IC equal to 0. So, you will have VAN, you can call it NN, that is voltage between these two, will be Zn, that is Zn we consider the impedance of the between two neutral into IN equal to 0, because IN is 0, it is the balanced 3 phase current. So, line current is the current in each line and the phase current is the current in each phase of the source or load. In star star connection, of course, line current is the same as the phase current, but of course, if it is another configuration, it may differ from from line to phase current like. Now, an alternating way of analyzing the balanced star star connected is to do on per phase basis. So, this circuit can be presented on per phase basis like between line to neutral, as you can see, and the single phase analysis yields to line current as I equal to VN upon ZY, and other line currents are also obtained from IA using the phase sequence, and single phase equivalent circuit of course of balanced star star connection shown here as a. So, now coming to the with the numerical problem, calculate the line current in the 3 phase system where all the data are given. You have a source impedance, you have a load impedance, and of course, you have a supply voltage which is balanced and load is also balanced here. So, it can be presented as a balanced network. So, we can say the 3 phase circuit shown in the figure is balanced. So, we may replace it with the single phase equivalent circuit and we obtain I equal to from single phase equivalent, where I equal to Vn by Zy, and Zy is your source impedance 5 minus J2 plus J10 plus J8, that becomes your 15 plus J6, and it comes like a 16.155 at the angle of 21.8 degree ohms, and from which you can find out of course the phase current is equal to line current, that is voltage of your phase voltage 110 at the 0 and the impedance 16.15 at the angle of 21.8 degree. So, it comes the current comes 6.81 at the angle of minus 21.8 degree ampere. So, in as much as the source voltage in shown in figure are the positive sequence, and the line current other phases also can be written like IB equal to IA at the angle of minus 120 degree, that is 6.81 at the angle of minus 141.8 degree. We are just adding 120 degree here, and IC equal to IA at the angle of minus 240, that will become your 6.81 at the angle of 98.2 degree ampere like. So, this is typical, I think just like a practice example of similar to as you have done earlier one, you can attempt in the same manner. Now, coming to typically a balanced delta star delta connection. A balanced star delta connection consists of a balanced star connected source feeding a balanced delta connected load, and this perhaps the most practical 3 phase system, as most of the 3 phase sources are usually star connected, while the 3 phase loads are usually delta connected, and it is to be of course, in 3 phase 3 wire system. So, it is to be noted that there is no neutral connection from source to load in this system connection. So, we can just have typically an example here. So, balance star to delta connection, as you can say load is delta connected and source is star connected. So, assuming the positive sequence, of course, the phase voltage are Vn equal to at the angle of Vp at the angle of 0 and Vbn at the Vp at the angle of minus 120 degree, and Vcn equal to Vp at the angle of 1 plus 120 degree. So, line voltages are equal to now Vab equal to root 3 Vp at the angle of 30 degree, that is called Vab, and we can call it Vp, Pc is root 3 Vp at the angle of minus 90 degree, that is we call it like a Vbc, which is across the load, we considering that there is no source impedance. And similarly, we can say Vc equal to root 3 Vp at the angle of 150 degree, that is equal to Vca, that is the voltage across the line of Ca. Now, the phase currents of course, in the load are now Iab, that is the current in this load, Vab upon Z delta, Ibc is typically this current, that is Vbc upon delta, and Ica is Vca upon Z delta. So, these currents have the same magnitude, but they are out of phase with each other by 120 degree and they are in virtually in the delta connected load phase currents like. Now, another way to get the phase current to apply the Kirchhoff's voltage law. So, applying the Kirchhoff's voltage law you can call it minus V n plus Z typically Z delta I a b plus V b n equal to 0, that is in this loop, and from where we can find out I a b equal to V n minus V b n upon Z delta or V a b upon Z delta or V a b equal upon Z delta, because there is no source impedance between the two. And similarly, the line currents are obtained from the phase current by applying KCL at the node A B C. So, we can say I a equal to I a line current is I a b minus I c a, I b equal to I b c minus I a b and I c equal to I c a minus I b c. So, since I c equal to I a b at the angle of minus 240, so we can say I a equal to I a b minus I c a, and that is I a b in bracket 1 minus 1 at the angle of minus 240 or I a b at the in bracket you can just change the polar coordinate to the, you can call it into rectangular coordinate and it becomes like I a b root 3 times at the angle of minus 30 degree or so. So, here also you can see the line current is again root 3 times the phase current in typically in delta connected mode like. So, we can say the magnitude of the line current relates to the magnitude of phase current as I L equal to root 3 I p, where the I L equal to I a equal to I b equal to I c and I p equal to I a b, I b c and I c a. So, phase diagram illustrating the relation between the phase and line current again is typically the example of this manner, and where you can have a typically again the sum of the two phase current which comes in the line current in this case also. So, we can say an again alternative way of analyzing the star delta circuit is to transform the delta connected load an equivalent star connection, and using the delta star connection again we can keep the Z y equal to Z delta by 3 and that becomes the per phase equivalent or so. So, now the example, a balanced ABC sequence star connected source with a V n equal to 100 at the angle of 10 degree is connected to a delta connected balanced load of 8 plus J 4 per phase. Calculate the phase and line current. So, load impedance is Z delta equal to 8 plus J 4, that is 8.944 at the angle of 26.57 degree ohm, and the phase voltage is V n equal to 100 at the angle of 10 degree. Then the line voltage is V a b equal to V n root 3 by 30 at the angle of 30 degree. So, it becomes 173.2 at the angle of 40 degree, V equal to V a b, that is load source voltage equal to load voltage, because there is no source. So, now phase current can be written I a b equal to V a b upon Z delta, and that is 173.2 at the angle of 40 degree divided by 8.944 at the angle of 26.57, that comes around 19.36 at the angle of 13.43 ampere. Similarly, you can write for IBC and ICA, only the all are equal except the phase difference of 120 degree. So, this comes as a your 19.26 minus at the angle of 106 at 0.57 ampere, and ICA becomes like 19.36, again equal magnitude and at the angle of again 120 degree shifted, that is root to 133.43 ampere. And the now line currents are typically like I equal to I a b root 3 by root 3 at the angle of minus 30 degree, that becomes 33.53 at the angle of minus 16.57 ampere. Similarly, for I b and I c you can have a same magnitude of 33.5, but angle difference is minus 120 degree apart, that minus 136.57, and I c is 33.53, that the angle of 103.43 degree at ampere like. And this you can call it, you can have a practice on the similarly on this example. Now, coming to the third case of balanced delta delta connection. Balanced delta delta connection is one in which both the balanced source and balanced load are connected, and goal is to obtain the phase and line currents. And so, you have a source also as a delta connected and your load is also delta connected. So, you can discriminate completely here the phase currents and line currents, of course, in source as well as load are different, but the you can call it there the line voltage will be the phase and line voltage are the same. So, assuming that a positive sequence, the phase voltage for the delta connected system is V a b equal to at the V p at angle 0, V b c at the V p at the angle of minus 120 degree and V c at V p at the angle of plus 120 degree. So, also V a b equal to V a b, load voltage, and V b c at the equal to V b c, that is again source equal to load voltage, and V c line voltage equal to the VCA. Now, the phase currents are Iab equal to VAB upon Z delta and equal to VAB upon Z delta and BC VB C by Z delta or VBC equal to Chan delta or IC equal to VCA Chan delta and that is VCA source voltage upon Z delta. Now, balanced delta connection, the line currents are also obtained from the phase current by applying the KCL at nodes ABC on the load side. So, IA will be equal to IAB minus ICA and IB equal to IBC minus AB and IC equal to ICA minus IBC. So, also each line current lags corresponding phase current by 30 degree. So, moreover this IL equal to root 3 times I phase current like as we got in earlier delta case. So, now with an example here, a balanced delta connected load having impedance of 20 minus J15 ohm is connected to a delta connected positive sequence generator having a VAB as given here. Calculate the phase current of the load and the line current. So, VAB is given 330 at the angle of 0 volt and answer is the load impedance as per is given Z delta equal to 20 minus J15 that is 25 in polar coordinate 25 at the angle of minus 36.57 ohm and VAB equal to load voltage equal to load line voltage equal to source line voltage and the phase now currents of course in the load will be IAB equal to VAB upon delta that is 330 at the angle of 0 divided by 25 at the angle of minus 36.87. This becomes 13.2 at the angle of 36.87 ampere. And similarly, we can say IBC will be equal to IAB at the angle of minus 120 degree that becomes 13.2 at the angle of minus 83.13 ampere and ICA will be equal to IAB at the angle of plus 120 degree and that is equal to 13.2 at the angle of 156.87 ampere. So, for a delta connected load, line current always lags the corresponding phase current by 30 degree and has a magnitude of root times that of the phase current. Hence, the line currents will be I equal to IAB into root 3 at the angle of minus 30 degree. This becomes like a 22.86 at the angle of 6.87 degree ampere. Similarly, IB will be as a IA at the angle of minus 120 degree and this also becomes 22.86 at the angle of minus 113.13 degree and IC also IA at the angle of plus 120 degree. So, that becomes again 22.86 at the angle of 126.87 degree ampere. This is practical example you can do in the same line. And now coming to the typically the another connection that is balanced delta star connection. So, a balanced delta star connection consists of a balanced delta connected source feeding a star connected load as you can see in the figure. So, again assuming that the phase sequence ABC phase sequence, the phase voltage of delta connected source is VAB equal to VP at angle of 0, VBC VP at the angle of minus 120 degree and VC equal to at the VP at the angle of 1 plus 120 degree and you have a balanced load of ZY connected in star. So, line currents are obtained in many ways. One way to apply the Kirchhoff's voltage law to obtain typically in this configuration minus VAB equal to plus ZY IA minus ZY IB equal to 0 or you can say ZY in bracket IA minus IB equal to VAB that is VP at 0 and you can find out IA minus IB that is a VP upon ZY or you can say IB equal to IA at the angle of minus 120 degree and then you can have a IA minus IB equal to IA at the 1 minus at the 1 at the angle of minus 120 degree or you can keep this polar coordinate to rectangular coordinate. So, it becomes IA into 1 plus 1 by 2 plus j root 3 by 2 that it becomes IA root 3 at the angle of 30 degree. Similarly, you can have this IA minus IB VP upon ZY or you can say IA root 3 into 30 VP upon ZY or IA equal to VP by root 3 into at the angle of minus 30 degree ZY. So, from this the other line currents IB IC are also obtained using the positive sequence. So, IB equal to IA at the 120 minus 120 degree, IC equal to IA at the angle plus 120 degree. Also note that the phase currents are equal to the line current in of course, in this case of star connected load. So, now coming to the example, the balanced star connected load with a phase impedance of 40 plus J25 is supplied by a balanced positive sequence delta connected source with a line voltage of 210 volt. Calculate the phase current and use AB as a reference. So, load impedance is Y equal to 40 plus J25 and that becomes in polar coordinate 47.17 at the angle of 32 degree ohm and the source voltage is VAB equal to 210 at the angle of 0 degree. So, when delta connected source is transformed to a star connected source, so we can write Vn equal to VAB at root 3 at the angle of minus 30 degree and it becomes like 121.2 at the angle of minus 30 degree volts. and now line current will be I A equal to V n by Z by. So, it becomes 121.2 at the angle of minus 30 divided by 47.12 at the angle of 32 degree. So, this becomes 2.57 at the angle of minus 62 degree ampere. Similarly, for I B will be I A at the angle of minus 120 degree, and this becomes 2.57 at the angle of minus 178 ampere, and I C equal to I at the angle of 120 plus 20 degree. This becomes 2.57 at the angle of 58 degree ampere, which are the same as the phase current in star connected load, and this is practice example on the same line. Now, coming to the unbalanced three phase system. An unbalanced system is caused by two possible situations. The source voltage are not equal in magnitude and or differ by phase by angle that are not equal, that are unequal, or load impedance are unequal. Thus, an unbalanced system is due to the unbalanced voltage source or unbalanced load. An unbalanced three phase system are solved by direct application of maths or node analysis, what we discussed already earlier in the DC circuit like. So, to simplify the analysis, balance source voltage, but an unbalanced load is considered here. So, we can say since load is unbalanced, so Z A, Z B, Z C are not equal. I mean these three impedance. So, line currents are driven by Ohm's law, that is I equal to V n upon Z A, or I B equal to V B n upon Z B, and I C equal to V C n upon Z C. And you will find here the three sets of unbalanced line currents produce the current in neutral line, and which is not 0, and as in case of balanced system, like the Kirchhoff current law at the node n give the neutral line current I n equal to minus in bracket I A plus I B plus I C, and that sometime becomes the substantial current. So, in three wire system where the neutral line is absent, so one can still find the line current I A, I B, I C using mass analysis at the node n, and KCL must satisfy in a, so that the I A plus I B plus I C will be 0, because neutral is not connected. So, same could be done for unbalanced delta star or star delta or delta three phase system. Now, coming with an example, the unbalanced star connected load has a balanced voltage of 100 volt and Acb phase sequence. Calculate the line current and the neutral current here. So, we have here Z A equal to 15 ohm, Z B equal to 10 plus J 5 ohm, and Z C equal to 6 minus J 8 ohm. So, line current will be I A equal to line voltage, that is your 100 at the angle 0 divided by 15. So, current is 6.67 at the angle of 0 ampere, and I B equal to 100 upon 100 at the angle of 0 plus 10 plus J 5. So, this becomes 8.94 at the angle of 93.44 degree ampere, and I C 100 at the angle 0 divided by 6.J8, that is your 10 at the angle of minus 66.87 ampere. Now, from this current in the neutral wire will be I n equal to in minus I A plus I B plus I C equal to 0. So, putting this, you will find the neutral current is Z 10.06 at the rate of 178.4 degree ampere like. Now, coming to second example, in a three phase 4 wire system with the line voltage of 400 volt and a non inductive loads of 10 kilowatt, 8 kilowatt and 5 kilowatt are connected between the three line conductor and the neutral. Calculate the current in each phase and the current in the neutral wire, because it is a unbalanced load. So, now we can find out the voltage to neutral is V line by root 3, that is 230 volt, and if IR, IB, IY and IB are the currents taken by 10 kilowatt, 8 kilowatt and 5 kilowatt load respectively, then we can find out IR equal to 8 into 1000 by 230. It comes like a 10 kilowatt means 10,000 watt divided by the voltage. So, it is a 43.5 ampere. IY will be 8 into 1000 divided by 230, 34.8 ampere, and IC equal to 5 into 1000 230, 21.8 degree. And this is along with the phasor. You can just see the phase diagram of the three currents are, of course, all three currents are unequal, but of course, with the equal angle. So, the current in the neutral is the phasor sum of the three currents, and in general the most convenient method by adding quantity is to calculate the resultant horizontal and vertical component, and the horizontal component is H equal to IY cos 30 minus IY IB cos 30. It comes your 0.863, 34.8 minus 21.87, that is 11.3 ampere, and vertical component of all three currents comes IB equal to IR minus IB cos 60 degree minus IB cos 60 degree, that is 13 ampere. So, current in the neutral will be IN under root of 2 component which are quadrature, that is 11.3 square plus 13 square, that is 17.2 ampere. So, that is typically the neutral current I mean in this circuit which flow through the neutral because of unbalanced load. Coming to third example, a delta delta connected load is arranged in the figure. The supply voltage is 400 volt at 50 hertz and calculate the phase currents and the line current. You can see the unbalanced load, 2 are resistive load and 1 is typically capacitive load, but equal voltage line voltage applied there. So, now coming to the solution of it, since the phase sequence is R by B, the voltage having is positive direction to R by leads 120 degree and that having the positive direction from Y to B, and V R by is a 120 degree and from V by similarly V by B is 120 degree in front of V R. So, if I 1 I 2 are the phase currents in your R by Y B and V R respectively. So, I 1 will be 400 by 100, that is 4 ampere in phase with the your V 1, and I 2 will be 400 by root 20 square plus 60 square, that is 6.32 ampere, and your I 2 legs are by angle phi 2. So, phi 2 will be tan inverse 60 by 20, that is 71.3 degree, and I 3 will be 2 into 3.1450 into 30 into 10 power minus 6 into 400 in the capacitor, that is 3.77 and leads by 90 degree from PBR the voltage across it. So, now if the current IR in conductor R is assumed to be positive when the flowing towards the load, the phasor representing this current obtained by subtracting I3 form. So, I2 square is your typically 4 square plus 3.77 square plus 2 into 4 into 3.77 into cos 30 degree, that is 56.3, or you can call it IR will be under root of this, that is 7.5 ampere. So, the current in line conductor Y is obtained by subtracting I 1 and I 2 as shown separately in the typically in phasor by an angle I 2 and I 1 reverse. So, phi 2 minus 60 is 11 degree with 30 degree second, and we can say I y square 4 square plus 6.32 square into 2 into 4 into 6 cos 11.34 degree, that comes 105.5, and from this under root of this will be I y, that is 10.3 ampere. Similarly, the current in the line conductor B is obtained by subtracting I 2 from I 3 as shown in the figure, and angle 2 is reversed. So, 180 minus 30 minus 11.30 degree, that becomes 38 degree at the 26. So, I B square is 6.32 square, 3.7 square, 2 into 3.7, 6.32 into cos 38 degree and 26 second, that is 18.5, and I B will be root of that, that is 4.3 ampere. And these are again you can solve this as a practice example to previous one. Now, these are the sum of the unsolved problem which you can just for your typically practice you can have a solution of these like. So, typically these are the references, I mean the books text which from which we have taken the material of this lecture, and thank you very much.